Slope fields. Slope fields. Slope fields. Does it sound complicated? Is that what you said? Sounds complicated? Oh, parts of it I'll explain, and you're like, oh, I totally get that. And then there's like one or two that are like, oh boy, here we go. Okay, so hang tough on a Friday. I know. Slope fields. Did you see me getting wound up there? Putting the music on, getting all the energy I have left, ready to rock and roll for you here. Slope fields and Euler's method. It's pronounced Euler. E-U-L-E-R. Legend has it that the University of Edmonton had a hockey team. And they called them the Edmonton Oilers. It's pronounced Oilers. Differential equations. Okay, this is where it starts to really heat up. Like, literally, okay, so when my daughter went off to university, for just a moment I thought, is it going to happen that she's going to take something at university, come and ask me, and I'll have to say, I don't know. Yeah? And I'm like, no, I'm not going to let it happen. I refuse. I'm sticking right with her. So I went through all my old books, and I got out this thing, and I started studying differential equations, because I knew that's, if there was something that I needed some practice on, it was differential equations. So when I get bored between everything else, I'm busy working on differential equations, so I'm ready. This is differential equations. And for those of you in physics who are upset, you should be upset. After all that, you're like, oh, well, neglecting wind resistance, or neglecting friction, or these things that we do in all the courses and say, well, we can't deal with that yet. Here we go. Yeah, this is getting us ready to be able to deal with all of those things inside equations. So an equation involving a derivative is called a differential equation. And for a while, we'll stay really simple, he said. It's not simple. It's not simple at all. It's really, really difficult. But we'll keep things under control so these differential equations don't go completely nuts. Little definition here. The order of a differential equation is the order of the highest derivative involved in the equation. For a while, we'll just deal with first derivatives. And then, of course, as you know, it'll heat up from there. And we often can use our knowledge of antiderivatives to solve differential equations. Often, really. Antiderivatives are going to be our method of solution for finding answers to differential equations. It says complete on a separate page this differential equation. It says solve this thing, and apparently we already know enough to solve some differential equations, and that's true. I got this ready to go on a separate page. Is this the right one? dy by dx equals secant squared 2x plus 5. And I'm going to explain this in two different ways sort of at once. We have to find a function whose derivative is secant squared plus 2x plus 5. There's lots of ways to sort of handle that. You might be able to just write down the answer. You might look at it and go, oh, I know what these ones are. But the way I'm going to start to handle it is just say, well, that means y is the antiderivative, and this is what I was trying to say somebody earlier who was having a little trouble with these, is we use this symbol without any limits on it, without any numbers top and bottom to say, we're just trying to find the antiderivative. Don't get too excited about from where to where. For now, I'm just after the antiderivative. So this symbol has another purpose to it that we didn't see in the previous chapter, with no limits of summation on there. Now, with no limits of summation on there, that constant is back, and you're going to see exactly why it's back here. For those of you who go, and you would go after this question and go, well, I don't need to write the integral symbol there to do this question. I just sort of think in my head, what functions has a derivative of secant squared? What function has a derivative of secant squared? Tan. So earlier we talked about whether the inverse trig functions would appear in homework. And they do appear in the homework. You don't have to do them yet because I haven't addressed that. And then I'm going to have to go back and find all the homework questions for you when we get to it. But the regular trig derivatives are in. Derivative of tan is secant squared. Derivative of 2x, hopefully that's coming easier now when you see things like 2x. And they like putting 2x in there just as a nice little warm-up to antiderivatives. And then the derivative of the antiderivative of 5 is 5x. Now, the question itself gives a little hint about how you're supposed to handle this. It says, find all the functions. See, when we had limits of integration, we didn't have to worry about that constant anymore. But there is a whole bunch of functions that have this derivative. That is, I could put a plus 10 here, and its derivative would be secant squared plus 2x plus 5 plus 0. I could put a plus 42 there, and they would still have the same derivative. See, there's a whole family of functions. That's the word we use. A whole family of functions that have this derivative. So all we do to handle that is we say, there's some constant out there. There's some number out there that we can put, and we got our choice of what number to put there. And if you're worried about that choice, don't worry. I'm going to turn right around in a second and deal with this constant and show you how we deal with this constant. But there's all sorts of functions that have this derivative. And they are tan x plus x squared plus 5x plus any constant you want is an answer to the question. And that's why they said find all the functions. There they all are. Any questions about that example? Why is this called a differential equation? Because it's an equation that's got a derivative in it. Okay? Do that example. I did that example. Okay. Initial value problems. In the previous example, notice how the solution is an entire family of functions. In order to find a unique solution to a differential equation, we must be given more information. That is, if all the information you receive is what I just showed you there, you're stuck with the constant. You're stuck with a family of functions. You're stuck with a whole bunch of different functions that have that derivative, and you don't know which one it is you're talking about. As long as the solution to the first order differential equation is continuous, all we need is one single point. If they just give us 1 point on the function, if it's continuous, then we will be able to pin down the solution, and we'll know which of these solutions to use. This point is called the initial condition, even though it might not be initial. It might not be h at 0. It's just like a starting point you could put in. It's a weird choice for a phrase in math to say initial condition. It doesn't have to be at the start. It can be any point on the curve, and it will pin down the solution for us. So a differential equation with initial condition is called an initial value problem. And the unique solution to an initial value problem is called the particular solution. And I'll use all these words in practice in just a second, and immediately they go right to another example. I get to practice some more antiderivatives, and I get to actually solve the problem. Do I have it here on my screen? There it is. New differential equation problem. dy dx equals e to the x minus 6x squared, and then I'll just pretend I didn't see this, okay? This is graph point goes through a certain point here. I'll just ignore that for a second. So if dy dx equals e to the x minus 6x squared, then y is going to be the antiderivative of this. I don't have limits of summation. So when I go to find the antiderivative of this thing, I'm still going to have to deal with this constant. The constant usually cancels nicely for me and disappears, and we don't even notice it. We don't even take it into account. But we need it here. Okay, one at a time. Antiderivative of e to the x. What function has its derivative? E to the x. E to the x, yeah. It's nice. It's nice when it appears as a derivative. It's nice when it appears as an integral. It's really nice. And then minus 6x squared. Well, just to do it in reverse, so if the powers get bigger or weird, you know, you have a plan. The plan is write down what you know the x is going to be. It's going to be x cubed. I added 1. Then I take this 3 that I'm going to have to multiply by, and I divide the coefficient by that 3, so I get the right coefficient out there. Other people handle that differently. They just go ahead and start choosing numbers in their head and find the number that works right. But that's the actual A to Z steps to doing them. And because don't have limits of summation here, I don't know exactly which integral I'm talking about or what values, then I've got this constant. I don't know how high or low this thing is. So I've got this constant out here. And that would be the end of the question, except it goes, whose graph point goes through 1, 0. So then you say, well, when x equals 1, y equals 0. And this goes all the way back. Now you see the foundation we were laying. We were playing with this subbing in to find a value all the way from grade 9 on. We had all these questions where we had to do this subbing. And even the ABCD stuff that I threw out there at you last chapter was on the test. It's all about this too, knowing how to sub in and find these missing values. So I sub in x equals 1, y equals 0, so I get a 0 over here. I get an e to the 1, and I get a 1 cubed. And so I get e minus 2. And so I get 2 minus e when I move it over. C is 2 minus e. Therefore, y equals e to the x minus 2x cubed plus 2 minus e. So this is the general solution. And this is the particular solution. It's the one that fits everything they asked in the question. So if you wanted to picture all this, I don't know what the graph of e to the x minus 6x squared looks like exactly, but there were many choices. So if this is what e to the x minus 6x squared looks like, I had all these choices. Oops, I didn't do a very good copy of that here. I know what I'll do. I'll use a function I have on these. Go to here, and I'll just make a bunch of duplicates of this while you're copying. Where's duplicate? Duplicate, 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 duplicate. See? There's all these choices I had. Oh, has it joined them all together on me? All right. I got to pull them apart. If only I could draw better, then I wouldn't have to fight with these things. Take your time. This is what I say to my kids on getting them to draw things. Just slow down. You're good at drawing if you just slow down. You know, there's all these choices that all have the right derivative at the right time. Then they gave me a point, and I went, oh, it's that one. Now I know which curve that I'm talking about here that has the right derivatives at the right time. But not only that, goes through the exact right point. One point's enough as long as this is continuous. You're like, why are you making a big deal about that? Well, you'll see in an example coming up. More time here? Did I give you enough time while I was fighting with my drawing? You're good? And we talked about that. Initial condition, initial value problem, particular solution, yeah, and I did that, okay. Notice how the condition pins down the solution curve. It grabs one. As long as the solution curve is continuous, the initial point will pin down over its entire domain. What happens if the solution has a discontinuity? If the solution curve is discontinuous, if you've got two different pieces, you're going to need a point on each part to be able to pin down both curves. Okay? Because you don't pin down the whole curve when there's two pieces to it. Yeah, the other piece might be like, oh, I'm going to move up here. And so it's a technicality, really. This doesn't come up a whole lot. But I just wanted to warn you that if it's discontinuous, you might have to deal with multiple points, one for each section of the graph. And then your solution will only have, will only be good for a specified domain. Well, just let me draw a little picture just to establish that. How is it possible for the initial condition to pin down only one piece? Say we had a graph and it was discontinuous. You know, so it's got two different pieces like this. And I'll just draw only two copies of it. But I want you to think that there's multiple copies of each of these. And there's a discontinuity here, just a complete missing part of the graph for whatever reason. The electricity turned off for a while and then it came back on. And you are given an initial point, and you go, okay, well, there's a point right there. That point pins down and says, oh, we're not this curve, we're this curve. But then we go over to this part, we could be down on this part again. You know, this part might have a different C value. Because it's discontinuous, it doesn't have to be connected up. When they're all connected up, you nail it down with 1 point. When it's discontinuous, you need 1 point for each section of the graph. I'm not setting up for a crazy test question. I'm not. I just want to mention that. Yeah, that's important if it's discontinuous to have multiple points, or else you'll have to specify the domain of your solution. Oh, and immediately right to another example. Good. All right. Hey, don't even start. I don't want any help. Back to here. Back to here. Is this it? Find the particular solution for dy dx equals 2x minus secant squared x passing through the point 0, 3. So my y, my general solution, will be the antiderivative of 2x minus secant squared x dx. There's my general solution. And so I get y equals x squared minus tan x. Don't want to beat this to death, but when you're finding general antiderivatives like this, we don't know which antiderivative we're talking about. So we need this constant out there, because that function, if we take its derivative, will have that as its answer. But then I need my initial condition when x equals 0. y equals 3, so I get 3 equals 0 minus, tan of 0 plus c. Oh, what's tan of 0? Sine of 0 over cos of 0. Cos of 0 is 1, and sine of 0 is 0. That's also 0, so 3 equals c. Therefore, y equals x squared minus tan x plus c is the particular solution. It's no longer a family of solutions. I know exactly which solution I'm talking about. Not C. Why did I write C there? That's not C. I don't need C. 3. Yeah? I now know exactly what number I'm talking about. 3. Questions about that? I haven't added too much here, actually. It could be in the previous chapter. All I'm doing is antiderivative, sub a point in to find that constant that we didn't have to worry about before because we had the limits of integration, so the constants actually canceled in the middle of all that. They didn't really become a part of the calculation. More time here? Is good? I saw a couple of frowns out there. So if you got questions, you let me know. Maybe the frown is just because it's like, it's Friday and I'm running out of steam. Use a calculator to graph 7 of the functions that solve the differential equation dy by dx equals cos x. How are the graphs related? Calculator. Graph. Menu. 5 for graph. Back to the screen I'm looking for. Is this the right screen? Yeah, there it is. dy by dx equals cos x. Okay, what function am I putting in here? If dy dx equals cos x, like the derivative is cos, what was the original function? That is, what's the antiderivative of cos? Sine. So I go y equals sine. This happened to somebody already today. They got a wrong answer from something they were doing earlier. Let me just go back out here and go menu 1 into the setup menu, radian mode. Yeah? Always radian mode unless they tell you degrees. From now on, it's always radian mode. So I just wanted to check that out first. Menu 5 for graph, yes. Y equals sine x. Draw. There's sine x. There's one of the graphs that solves this differential equation. But there's plenty more. That is, I could have used y equals sine x plus 1. And actually, I'm going to put y equals sine x minus 1 on the same graph. It said graph 7. I don't need 7 to do away with this point. I mean, you can graph all you want. But I really want to show you something that's important to understand the next part. The part that looked complicated in the notes. But if I explain this just right, it might clear up some of the problems in all that. So enter, draw. So now I've got the two sine x graphs. Now let's talk about the slope at any particular x value. Notice that at this x value here, they both have slope 0. At this x value here, they both have slope 0. At this x value here, they both have slope 0. That's what we mean when we say there's a family of curves. See, there's two different curves that have the same slope at every particular x value. You pick any x value, and these two curves will have the same slope every single time. And if you go to, I just can graph a whole bunch more of them. You can graph 7 of them on the screen there, and every single one will have the same slope. I'm going to draw a few more on there, though, because there is an idea I want you to see. Okay, yeah. So y equals sine x minus 1. Okay, I also want, let's say, sine x. And sine x plus 2. And sine x minus 2. I'm just going to go back to my graph and see if that gives enough to give the idea I want to give. Yeah. And what we get is sort of a slope field, yeah, where you can see what the slopes would be at any particular time. That is, as you look up here, all of those slopes have these same values all the way along. And it gives you a picture of what all the slopes could be at any particular time. without actually, see, this picture doesn't actually solve the problem per se. It just shows you, hey, if you're at this x value, you're going to be heading down. At this x value, you're going to be heading up. You know, it really shows you what to do next, what direction to go. If you want, it's like a map, a road map to say, if you're here, go up. If you're here, you're going to be going down. You know, okay. Just introducing that word. Okay, did I do that? Yeah, I did that. Okay. Sometimes, this is the most important sentence that you've seen all week. Sometimes we are unable to find the antiderivative. So a lot of the methods we've been toying around with here, you might be like, well, why would I go through all that if I got the integral? Sometimes we are unable to find the derivative. Not just you, AP calculus students. Anybody on the planet can't find an antiderivative of this thing. It's not easy to find antiderivatives. We can know they exist, but maybe we can't find them. And that's where some of these methods come in. So we can still find a solution to any problem using the fundamental theorem of calculus. Here it is, fundamental theorem of calculus, part 1. Recall that if you've got some function that's an integral, if you take its derivative, and the lower limit's a constant and the upper limit's just x, you can just sub x into the function and get your answer. Okay? If you haven't practiced a bunch of these, maybe this isn't entrenched yet, so let me go over it again if you haven't practiced a bunch of these. The fundamental theorem of calculus, part 1, says if you've got an integral with lower limit, any number you want, any constant you want, an upper limit x, its derivative will just be the function with the x subbed in. This comes from the idea that if you've got an area and you want to see how much the area is changing, it's just changing by the function value there. You're just adding on a little bit. So it says find the solution to this thing. And I was talking earlier with 2 different conversations where we got to a differential equation that we couldn't find the antiderivative. Finding the antiderivative of y equals e to the negative x squared is a major league problem. And if you look at it and go, oh no, I can do it, just try a few where you think, oh, I'll just do this, I'll just do this, then take the derivative and you'll find you'll keep having a problem. It'll keep slipping away on you. It's a major league difficulty. However, I can build a function whose derivative is e to the negative x squared. Okay, here I go. I'm going to build it. Y equals. I don't want to write that high because I might have some more notes to do, so I'm going to go a little higher. One more dot there. Stop it. There, okay. Y equals. And my move is to go, I can't do this integral. I can't do this antiderivative at this point in my antiderivative career. So I'm going to make up a function that is an integral. My integral, when I take its derivative, I can use the fundamental theorem of calculus to get the answer. So what has to be here? I need an x up here. And then I need an a down there. I'm just going to write a down there for now, okay? We'll decide on that later. Maybe it's a 2. Maybe it's a 5. Maybe it's a 9, 11, 0. It doesn't really matter. But I'm not going to fill it in yet because to finish this question, I've got to choose a very specific one. Okay, but any number will do there. Then I need this thing inside there, but with a different variable. Let's just see if this works. This is what will appear in the fundamental theorem of calculus. Part 1, homework, is you'll look at something like this and try and find its derivative. And you go, oh, is the lower limit a constant? Yes. Is the upper limit x? I'm like, okay, answer, just sub it in, e to the negative x squared. See, it's not the kind of function we're used to seeing. So when I said we couldn't find the antiderivative, we're going to make up something sort of special to be able to solve these problems. Plus c, though. Huh? Plus the constant. So how are we going to find the constant? I've got to sub in 7 and get answer 3. This gives me some help. You can really struggle with these if you don't choose a really smart, really, really unbelievably brilliant, smart value for a. And this came up in some other homework, came up in another lesson. I believe it was a video, but my old brain runs together and can't remember if it was a video or live that we talked about this. There's something about this situation up here, f at 7 equals 3, that tells me a brilliant choice for the lower limit of summation. Do you remember what I'm talking about? Did I bring this up again? This is why I put this in another video or another lesson, is because maybe you need to see it twice before you sort of remember what the really cool move would be. Emmett likes 7. Yeah? He likes 7 in there. Let's just fast forward and just imagine he's guessing for a second. And let's just see what the result of that is, that choosing of 7. Now, I've got my function. I'm going to use this information up here. When x equals 7, y equals 3. And we'll use his 7 as if he knows what he's talking about. And let's just see what happens. And hopefully by the end you'll go, oh, that 7's good. That was a great 7. That was a lucky 7 he put in there. Y equals 3. Integral 7 to 7. Yeah, because I just sub in x equals 7. E to the negative t squared dt. Which I still can't find the antiderivative of. So I couldn't evaluate it. I couldn't possibly evaluate this thing because we're right back to the same problem again, trying to find the antiderivative of e to the negative t squared. The whole reason we're using this method is because we couldn't do that. But Emmett's awesome choice of a lower limit allows us to go, I don't have to do this antiderivative. What's the integral from 7 to 7 of anything? 0. What a great, that is a smooth move. I don't know the history of this problem. I don't know. I can just imagine this sat on the shelves for 50 years collecting dust. I'm like, what are we going to do? And then finally somebody walked in and said, well, why don't we just use the 7 down there? I'm like, oh, yeah. That solves the problem. Now I got the constant. So my function, therefore, y equals integral from 7 to x e to the negative t squared dt plus 3. Is a great choice for a function whose derivative is e to the negative x squared and whose and where f at 7 equals 3. Brilliant stuff. Brilliant stuff on a Friday. Still got 40 minutes, do I? I'm not going to be that long. If you're like, oh, you're really going to go on for 40 more minutes? No, I just want to make sure that I'm going to make it. We good here? Need more time? This is a tough question. I'm not acting like, oh yeah, you totally get it. I can do 100 of these now. No. It's on the video. It's in your notes. Now when you get one that's like, how are we supposed to do that integral? Maybe the fundamental theorem of calculus. He's in the corner going, come on, put me in. I can do it. Yeah? Not the craziest algebra we've seen either. Yeah? And a couple of people in regular calculus just emailed me some questions from tough derivatives. A chain inside of product with a quotient in there, and they're like, and they're freaking out. This ought to be a nicer algebra here. This isn't so crazy, but it's tough thinking, like your brain's got to be on full speed to be able to handle these things. All right, where was I? Did you see? Yeah, I did that. Okay. Oh, solved that crazy question. Yeah, okay. Oh, slope fields, changing topics, essentially. Slope fields. Not really. I tried to lay the foundation. By thinking about slope, we can produce the family of solution curves for differential equations without actually solving the differential equation. There are differential equations out there that we cannot solve. Not we, AP Calculus. I mean, we humans on the planet Earth haven't been able to solve these differential equations. But we can still get pictures of the answers without actually solving the equation. How do you do that? Here, let me show you. Consider the differential equation dy dx equals cos x. We know that dy dx gives slope. We know dy dx gives slope. So we know if we sub in an x value of 0 in here, when x is 0, the slope must be 1. Okay? Not much information there. Don't let it freak you out. You're just saying, I could find the slope at a particular x value without solving the equation. Now you're like, I know how to solve this equation. I know. We're practicing on an easy one. But let's say we couldn't. We don't know what the antiderivative of cos is. We can't remember what it was. We can't figure it out. We could find the slope at x equals 0. So the slope at x equals 0 is 1 regardless of the y value. And we can illustrate this by doing small line segments. We go, I don't know what the answer is, but I do know when x equals 0, the slope will always be 1. So, I don't know what the answer is, but I do know if your x value is 0, you better go this way. It's like an arrow. They should maybe have little arrows and go this way. Yeah? Similarly, at pi and negative pi, so if I put pi into this, I get 1. And, sorry, at pi I get negative 1, and at negative pi I get negative 1. So we know that the slopes are negative 1 at those values. See, we're just getting a picture to say, if you're at this x value, your slope must be this. I don't know what the solution is. I don't know what the equation is, but this is what it looks like. If we do the pi by 2s, we get zeros. And now can you see sine developing there? Here, let me just guide you through one of these. Down, up, down, up, down. Sine's laying in there, screaming out, it's just me. Yeah, sine, what are you doing? But if we couldn't do it, this would be the way to go. If it was some crazy thing, sine of x squared, e to the negative x squared, e to the x to the power 4 over sine x cubed plus some just giant mess. You go, hold on. I can get a picture of the solution without actually solving the whole deal. A few extra slopes there so you can really start to see sine. Do you see how it doesn't line up nicely though? You got to really visualize. This is tough to visualize because look, it goes here, but can you sort of see a sine curve mapping out through those things? But it doesn't quite line up because it doesn't give, it should give all of the different x values. You can imagine that a higher resolution would really help here. The above graph, called a slope field, gives an approximation of the differential equations family of solution curves. A better way to say that is the slope field shows the slope at any particular x and y value. Okay. Oh, I clicked that. No, I can't click this. Okay, good. Another example. Consider the differential equation dy by dx equals x plus y. Use your calculator to construct the slope field. Okay, get your calculator out. And this is one of those things you got to follow the instructions again with me, okay? Because the calculator on the screen won't do this. Oh, hang on. It'll do part of it. I'll do the first part with you, and the second part, well, you have to do on your own calculator. So, go into menu 5, into the graphs. If you've still got graphs on the screen, if you're following along with me, hit your F6 button to get back to this, and then delete everything that's in there. If you got some things in there, just get them out of there. We don't want anything in there anymore. And I know this says y equals, but the program I'm going to show you interprets these as y primes. So, for this question, just imagine this is a list of y prime. You're like, it's not a list of y prime. I know the program's going to think it's y primes. These are all y primes now, okay? I'll just cast a spell. Woo, woo, woo. All your calculators think these are y primes right now. Okay? And it wants the derivative to be x plus y. So I type in, stick with me, x plus, and you're like, how do I type in y? It's over top of the subtract sign. Do you see a little pink y over top of your subtract sign? So you go alpha, subtract sign, and you get x plus y, which normally is a big problem. Normally your calculator is like, y equals x plus y. What are you doing? But it's not y. It's y prime. You're like, how can it be y prime? The programmer took care of it. Okay? It's going to be fine. Don't worry about a thing. I'll show you in a second. Okay, so y prime equals x plus y, execute. Then we go back to menu and go over to program. I got no programs. I can't have it on here. So now I got to walk through it with you. So I'll do it on my screen here. Okay, so I got to do the other part that you already did. Menu 5, F2, F1, get rid of that. X plus shift negative, so whoops, alpha negative, x plus y equals, okay, menu, program. You with me? You're on programs now, and you see on your screen Euler's method, which is later in this lesson, still coming. Riemann sums, which we already learned about, and slope field. Go down to slope field and press enter. It says store dy dx in y1. We did that, yeah? It says that's where I'm going to look for dy dx is in y1, which we already put in there. And then it says just press 3 after you've done that. Why the number 3? I have no idea why whoever programmed this. Then press 3 and then just wait for stuff to happen. Now, if you don't get something that looks like this, it's because your window might have been off a little bit. So then I want you to hit V window. Mine's still going. I don't know about yours. Mine's still trying to think this thing through. It's doing a lot of calculations. I'll show you the calculations it's doing in a second. Hit V window. Change X min to -10. Change X max to 10. Change Y min to -10. Change Y max to 10. Then exit that. Go back to slope field. Press 3. And you should get a better picture. Takes forever though. Look at it. It is grinding. Mine is just grinding through this, trying to get all these answers. You know what it's doing? It's going x0, y1. Sub it in, draw a little line. x1, y1. Sub it in, draw a line. x2, y1. Sub it in, draw a line. With more computing power, obviously this would work a lot better. Did it come up? Did you get the crazy graph? Were you able to fix the window? Did you have any problems with the window? Are we good? Everything's good? Okay. Now we've got a picture of what's got to happen to the slopes. That is, if your x value is here and your y value is here, that should be your slope. These are all the different slopes. It's a slope field. It just shows what the slope would be at any particular x and y. Notice the following properties. Okay, and this helps with the question that's coming up, sort of a difficult question coming up. Notice along here. Do you see right there? See, small negative slope, small positive slope. So there's zero slope right along here. Yeah? That's the line x plus y equals 0, or y equals negative x, that the slope would be 0. Okay, so that's an interesting little attribute of this whole thing. Difficult to see. The slopes are -1 along the line x plus y equals -1. So where's the negative? That would be y equals negative x minus 1. See right there. See the slopes are the same all the way along there? This is difficult. It's difficult to see all these things, but I'm just trying to draw your attention to the advantages of slope fields. Now we can look at the slope field and sort of see what's happening in general. We get a picture of what's happening. Remember, this is a picture of all the possible curves that have dy dx equals x plus y, which, by the way, we cannot do the integral of, or the antiderivative of. Antiderivative of x is 1/2 x squared. Antiderivative of y, yeah? You see the problem with something like this, but drawing a slope field helps this. Also, okay, this is the best move ever. All that other stuff is fine, but I really want you to see this move. Take a look at this slope here. I'm just going to go straight along here and make my x values bigger and bigger. What happens to the slope as I make my x values bigger and bigger? Do you see what's happening to the slope of x? It's just getting more and more. Bigger values of x are going to give bigger values of slope. And the same thing happens with y. If I go straight up with the y's, look at the slopes. Bigger, 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 bigger. Along that certain x value, bigger values of y will give bigger slopes. All this reasoning has problems, though. Like, there's sometimes that you got to really think through these things. But in a reasonably simple example like this, you can walk through and do some thinking about what you see on the slope field. I mentioned that. Now, then if they give you a particular solution, they said the solution at 2, 0, 2, 0 right there, you could grab one and say, okay, that's what that curve would look like. We don't have the equation of it, but we could come up with the look of the curve and get an idea of what the curve might look like, what the solution for this might look like. Okay? Whew, those are tough. It only gets tougher. I think there's a matching one right after this. Oh yeah, match. I don't think that in any world that you would start to be ready to be able to, if I give you this, you could draw the slope field. No, not at all. But maybe, just maybe, we can match them up. Matching's a little bit easier. You know this from other classes, right? So I'm giving you a matching question, like, well, this won't be too bad. I don't need to know every answer to be able to match it up. I can just match up the ones I want. I'm going to try and do them in order, though. I'm going to, try and be a big shot on this on Friday here and try and just do them right in order. Because that's not, you do the matching, you grab one, you're like, I know this one. And you just match it up, and that eliminates other possibilities. I'm going to go right after it. dy dx equals x minus y. Here's what I know. When y and x are equal, the slope should be 0. So I'm looking for, when y equals x, that I should get slope 0. Does this one seem to have slope 0 along y equals x? And no, it seems to have positive slopes all the way along the way. That doesn't work at all. The next one, as I look along here, along y equals x, do I sort of see slope zeros in there? And I think maybe I do sort of see slope zeros. If you're not convinced, don't worry. I'm going to have other explanations here. But I sort of think I see that the slopes, when the y's and x are equal, I sort of see a 0 there. Because it certainly doesn't happen here. And it certainly doesn't happen anywhere here. There's no 0 slopes here at all. Making me sort of think, oh, possibly, this reminds me of me in history exams in high school. I never knew any of the information. But if they give me a matching, I'm like, well, I know this one doesn't go with that one. This one goes with that one. Ooh, got him, yeah? Second one, dy dx equals xy. Here's what I know. If the x values are 0, or the y values are 0, I should get slope 0 on both of those axes. On both axes, we should see slope 0. Let's see. Do I see slope 0 on the x-axis? No. Slope's like straight up. Do I see slope 0 along the x-axis? Oh, maybe I kind of do see slope 0 along the x-axis. Do I see slope 0 along the x-axis? Yeah, I think I sort of do. So I better check the y-axis. Y-axis. Do I see slope 0s here? No, the slopes look really upright, whereas here the slopes look like they could be 0s along the y-axis. You know, that kind of thinking. And I go, okay, then I think maybe this one's D. When there's denominators, that actually helps me. Me personally, I'm like, oh, good denominators. That makes it easier because I need undefined slope where y equals 0. That means I need straight up slope. I need vertical slopes when the y value is 0. So when the y value is 0, oh yeah, vertical slopes all the way across there. Vertical slopes here on this one all the way across? No, flat slopes all the way across there. And that allows me to finish up the matching. Would I put this on here and say, oh, just draw me a slope field for each of these? No way. Oh man, you're like, whoa, that is some heavy work to do. But a matching, there's a possibility there. I think there's another good question like this in the homework where you get to try and match them up. Don't cheat. Spend a lot of time staring at it and see if you can think these through. Last thing of the day, Euler's method. Earlier we graphed a particular solution to a differential equation by producing a slope field. We can actually graph the particular solution directly by starting at a given point and piecing together the line segment piece by piece to build a continuous approximation of the curve. That explanation is lousy. That is a lousy explanation of what's about to happen here. I'll be able to explain it really good by actually doing it here in just a minute. Euler's method. Begin at some xy. I'll go back to these instructions in a minute. I'll read them really fast. Begin at some xy. Find the slope at that particular point. And use that to come up with a new point. An estimate of what the next point would be. And this graph makes it look like you're going to be thrown way off here. No, we're going to keep the points really small. Then use your new point to graph a new point and so on and so on. Here, you got to see it in action. The explanations are lousy. Describing Euler's method isn't nearly as good as actually just doing Euler's method. Okay, I did that. We did that. Euler's method. Okay, here's Euler's method. This is a way of estimating other points on the graph without having the equation, just by moving across the graph. So they said start with f at 2 equals 0. So I've got my initial point of 2, 0. Here it is. 2, 0. With just that information, I can find the slope at that particular point. Because it said dy by dx is x plus y. So I just sub the x and y into dy by dx, and I go 2 plus 0. And I know then that the slope is 2 at that particular point. I know this function must be going up by 2s at that particular x value. So I'm just checking my notes because there was a misprint in one of these things. Okay, the second equation is where the misprint goes. Okay, I'm ready. Then it's told me delta x of 0.2. Now, if you think this method would be inaccurate, all you got to do is make this delta x smaller. 0.01, 0.001. Make it as small as you want, and we can get more accurate here. So don't worry about accuracy. We just chose a fairly small x so that we could be fairly accurate. Delta x is 0.2. And here's the big moment. If we're going to move over 0.2 on the x, and the slope is 2, then how much do we move up? Whatever the slope is times the delta x. You'd say, the slope's telling you how much to move up with every bit of x. So we just go dy by dx times the 0.2 is 0.4. So I've used the delta x multiplied by the slope to figure out the delta y. And now I've got my new point. 2.2, 0.4. Start at 2, go delta x 0.2. Start at 0 for the y, and add 0.4. Now, I got to tell you, now I'm just going to do that again and again and again. So if you're like, I'm not sure what you're doing at all here, just give yourself a number from 1 to 10 and go, okay, on a scale of 1 to 10, I'm about a 2. And then every time I do it, I'll just re-explain it, and by the end, you'll be bored, and I'll send you home. Okay? That's the plan. I got a new point. I started at 2, 0, and using the slope at that point, I went, oh, using that slope, the next point over is around 2.2 comma 0.4. So that's the point I'm going to start at and say, okay, from there I want another point. That is, if I take the 2.2 and the 0.4 and find the slope, because I've got the equation for slope. Slope says just add x and y together. So I'm going to add those two things together. 2.2 plus 0.4. The new slope is 2.6. At that x and y value, now the slope's 2.6. Delta x is still 0.2. That's what they suggest in the question. If you're worried about accuracy, that's fine. Just rebuild the table for 0.01s. It'll take you a lot longer, and you'll be a lot more accurate. Now to find the new y, I say, okay, the slope here was 2.6. We've went over 0.2, and that's enough to tell me how much up I went. I went up 2.6 times 0.2. I must have to go up 0.52. My new x value is 2.4. My new y value is now 0.92. Where are those numbers coming from? 2.2 is where I started. Go over by 0.2 to get to 2.4. Go up by 0.52 to get to 0.92. Go again. Now, apparently, my estimation of where we will be is 2.4 comma 0.92. I put that over here. 2.4 comma 0.92. To get the slope, now I pause to see if you're with me after 2 rounds. How do I get the slope? I've got an x and y. How do I get the slope? Yeah. It was at 0.4 before. The delta y said add 0.52 on. Now I'm up to 0.92. Good. Back to here. I've got an x and a y. How do I get the slope? Just add them together. That's what the equation says. It says to get the slope, add the x and y together. So at 2.4 comma 0.92, our solution will have a slope of 3.32. My delta x, they told me to use was 0.2. You want a more accurate answer here? Use smaller delta x's. You want to get there in some reasonable amount of time? You better keep your delta x's up a little bit. Now the delta y. I know I'm going over 0.2 with slope 3.32, so that tells me how to find how much y to change. That is, it's 3.32 times 0.2. And I think I get 0.664. These numbers are starting to get a little crazy enough that I want to check them as I go here. Not with that calculator. 0.2 times 3.32. 0.664. So my new x and y, I was at 2.4. I went over 0.2, so now I'm at 2.6. And then my y, I was at 0.92. Delta y was 0.664, so I add 0.92 plus answer. I get 1.584. See, I can get anywhere I want now with this thing. Euler's method says I can get anywhere you want on the graph and find all the points you want on the graph as accurate as you want. You say, well, this isn't very accurate. You're going over 5.2s. No problem. You want more accurate? Knock the x down to 0.00001. Take the 3.5 days it's going to take to build the table, and you get a perfectly accurate answer. And you computer people are like, oh, I can get a computer to do this. I'm going to show you how to get your calculator to do it in just a second, okay? And we'll check these answers. Because it's hard to concentrate all the way through here. I have the same problem. It takes a lot of focus to concentrate all the way through. Let me slow one level down here if you're confused, because a bunch of frowns turn into just calmness there in that last round where people went, oh, I see what you're doing here. I think that's what happened. I have a point on my solution, 2.6 comma 1.584. One step at a time. If at that point, how do I find what the slope is at that point? Just add them together. You've been given the slope equation. It tells you anytime you want a slope, add x and y together. And that's fine. If that equation is more complicated, no problem. We're just subbing into it. So I'm adding 2.6 to 1.584. And it's late in the day, so I better check these each as I go. Plus 2.6, 4.184. My delta x is 0.2. Now somebody else. Tell me on this level before I get to the last line of this. How do I get the y value? I started at 2.6, 1.584. I know I want to go over 0.2. I know what the slope is. There. How do I then find how much I should go up in the y? Yeah, multiply the slope by the delta x. Say, okay, just multiply it to get your estimate for what the y should be. And so I'm going 4.184 times 0.2 equals 0.8368. Again, late in the day, we're not going to trust my mental math at this point. 0.8368. And so now, one more time, how do I estimate the new x value? My old x value was 2.6. How do I then get the new x value? Add on the delta x. We were saying go over 2.6, so 2.8. How do I get the new y value? Take the y and add on the delta y. And so if you're still confused about what's happening here, notice that she's caught on to this. You know, you can tell that she's like, she knows exactly where to find all this stuff. So if this is stressing you out on a Friday afternoon, just attribute that to, it just needs one more look. 2.8, comma, 1.584 plus 0.8368. 2.4208. We'll go one more. I'm at 2.8. And if you're like, when are you supposed to end here? This is the last one, and look around to see how it is I know that this is the last one. So to get the slope, I just add those together. So I add 2.8 to that. 5.2208. Delta x is 0.2. Multiply that by 0.2 to get the delta y. 1.04416. And then I get 3, comma, add that to my 5.2208, and I get 6.26496. What questions do you have about that as I look at the clock and notice I'm down to 15 minutes? Maria? Great question. You okay with the procedure now? What the heck are we actually finding? Given a certain x and y value on a graph, yes, the graph of y actually, we know that the point 20 is on the graph. What we want to find is, what would the point be at 3 comma something on the graph? How we do that is we sneak up on it. We go, okay, well at 20, I know the slope is 2. So I'm going to go over a little bit and get a good estimate for the point at 2.2 and go, oh, I'll just use the derivative to map up to where the point would be at 2.2. Then I use 2.2 and I map up a little bit from there. And basically I ride the slope field to the next answer. And so let's look at a slope field. So maybe we know we're at, this is a good place to show the ride, you know? Because you're like here, and you go, well, I'll just go a little bit, I'll use this slope to go a little bit this way, and now the slope is that way, and now the slope is this way, and now the slope is this way, and I just follow the slope field around to find out what x and y value I get at some later point. X is 3. You're like, this is going to take forever. Well, okay, it's not long before we get computers involved here, to be honest. And let's do that now. Let's switch over to your calculator right now. I didn't test this out. So what I want you to do is go to menu 5. Oh, it's already in there, x plus y. We put that in there earlier, right? So that's good. We already got that in there as the equation, which is the y prime equation. The calculator is going to interpret that as y prime now. Now go menu program. I'm going to go slow, because if we finish this off, this will be the last example, and I'll tell you why it can be the last example in a second. Yeah? And hit slope, not slope field, Euler's method. Do you see it at the top there? It's not the top on mine. It depends on how it copied yours. Do you see EULERSME for Euler's method? It says initial x. What's our initial x? 2. Initial y? 0. Step size, 0.2. It says step number 1. Okay, step number 1. Hit execute again. It goes x coordinate. Did yours come up 2.2? Hit execute again. Y coordinate 0.4. Question. Oh yeah, okay, we'll fix that in a second. And makes a good point about the calculator, okay? He says there's an error here on the last section, I believe it. I got distracted. So, but let's walk through, because this is going to walk through every single step for you. It's going to show you all the answers. So I press enter again. It says step number 2, 2.4, 0.92. Do you see those? I'm feeling pretty good now, yeah? Hit again, 3. Step 3, sorry, 2.6, 1.584. Looks good. My table looks pretty good. Step 4, 2.8, 2.4208. And here's my mistake apparently. 3, 3.46. I made a mistake there. Let's cross that out to show the mistake. I was supposed to add y with delta y, and so then I should have got 3.46496. And that'll be the biggest battle in this. This procedure is not difficult at all. Can't be called difficult. We're just adding and multiplying and stuff like that. But it's hard to keep your attention span on there long enough not to make a mistake along the way. Did you get 3.46496 in your last step there? So nice. So I leave the next one. There's another one there with 2x minus y and x is 3 is 2. I use that as a practice one. I'll leave that in the note for you to try this one out, try the same procedure, but you've got your calculator to check your answers every step of the way. Don't wait till the end to check your answers, because if you made a mistake way up here, you got to erase all that. You know, every line, use the calculator to check. Yeah, for sure, because Euler's method is tied right to technology. Euler's method came along hundreds of years ago. But who, even a crazy mathematician, who's really doing much of this work? But then when technology came along, technology's like, ooh, I can take care of this really well. So you really want to see how this is used technology-wise, because halfway through this, you're like, is anybody really doing this calculation? Now without a calculator computer, they're probably not. Yeah, but you have to know how to do it. Yeah, it's got some big break problems, okay? And sometimes all you can do is turn your calculator off and on again and go again.
Yeah, I did that as well, and also didn't fix the issue. But if you go to memory and then just hit exit again, I think or you go back to memory and then I think it's
Yeah, right. Just be careful, because there's one in there that gets rid of the programs that are in memory, and then we'll have to reprogram your calculator. Yeah, it's not a perfect system. You can imagine how you computer people are going to be like, I'm about 2 seconds from chucking this calculator in the garbage, and I'll just write my own code. Because really, how much code is there here? How many lines of code here? 11? 15? Yeah, but this isn't a long program to be able to program a computer to do this. Okay, last thing. In general, does Euler's method give an underestimate, or does it give an overestimate? Or sorry, when does it give an underestimate and overestimate? I'm just going to draw. You maybe sort of know what's coming here. Again, it's tied to concavity. Euler's method is going to use the slope to estimate a new point, the slope of the tangent. So there's the slope of the tangent right there. And I'll draw another one on here. Another slope of a tangent. So Euler's method is going to just take a tangent slope and use that to estimate what the curve's going to do next. So when we're concave up, and when we're concave down, Euler's method is going to make a slight mistake. When we're concave up, Euler's method is going to underestimate where we should be going. And when we're concave down, it's going to overestimate. And the only reason I mention that is, in the middle of Euler's method, you're like, well, these numbers aren't going to be perfect. There's somebody out there who can improve on Euler's method and go, ooh, I'll use the double derivative to help my estimate. So I'm not just stuck to the single derivative. The double derivative will help me to go, oh, if the double derivative is positive, maybe I should be adding a little bit more to my answer than just what the single derivative has to offer. So double derivative has huge applications in all this.